everyone can hear me all right, but today I want to talk a little bit about what it would look like to do a double integral over a region that is not rectangular. So for some motivation, I wanted to discuss what does U substitution look like, right, in Calc 1. Substitution in one variable, right? This is a topic that we cover a lot in Calc 1. So I want us to sort of recall this topic just for some motivation. So say, for example, we were integrating something like x times sine of x squared dx, right? We learn in Calc 1 that the way to integrate something that looks like this would be to do a substitution, right? So if we let u be the inside function, right, when we're thinking about u substitution, you're really just undoing the derivative that comes from the chain rule, and so that inner function here is x squared, right? So if our u is x squared, we want to rewrite this integral from x to the new, more simplified integral in terms of u, right? So I want to take this complicated integral that you can't integrate directly and rewrite it as an integral in terms of a simpler integrand in terms of u. So how we do that is by taking a derivative, right? The derivative is 2x. After doing some algebra, we get that dx is du over 2x. So we substitute our value for u. And we also substitute in dx, right? So from Calc 1, we know that we would integrate x sine of u times du over 2x. Here the x's divide out, and we're left with a 1/2, which I'm going to pull out of the integral. And here we're finally just integrating something that's a lot more simpler in terms of u. To find the antiderivative of sine u, we know that's negative cosine u plus c, and then subbing in our u back into our antiderivative. The answer should be negative 1/2 cosine of x squared plus c, right? So this is sort of the usual substitution that we learn in Calc 1. But what if we were to maybe rethink how substitution works? Same problem, integrating x sine of x squared dx. And we want the same idea, right? You want to undo the chain rule, so we would allow u to be the inner function. So this gives us that u is x squared. But conversely, this also means that x is the square root of u if we solve for x, right? And so if we take a derivative here of x with respect to u, dx over du is 1 over 2 square root of u. Right, we know what the derivative of the square root of u with respect to u is. And then solve for dx, which is 1 over 2 square root of u du, right? So this is a very different way to do substitution. You're now subbing in dx in terms of u. So what do we actually get? Integral of, well, x is the square root of u. Sine of x squared is u. And then the dx, which is 1 over 2 square root of u du, right? Oh, that should be a u. The square root of u divide out. You can pull out the 1/2. And you're left with the same antiderivative that we had earlier, right? Negative 1/2 cosine over u, which is x squared plus c, right? So you're still doing the substitution rule, but we've written x in terms of u and taken a derivative of x in terms of u instead of how we normally do, right? The substitution. So hopefully this provides a little bit of motivation as to what the substitution would look like in higher dimensions, right? In 2 variables. So let's move on to that part. How would we do the substitution in 2 variables So the general idea, I should write down a motivating example. Let's evaluate this double integral over region R, which I'm going to, actually I'm not going to call it R, I'm going to call it region D, which I'm going to show what it looks like on a graph later. So let's find the double integral over the region D of x minus 5y dA, where R is this region. Let me draw it. It's a parallelogram. So we'll have that it has vertices 0, 0. One, 0, 2, 2, and 3, 2. So this is the region D. It's this parallelogram, right? So thus far, at this point, students have learned how to find the double integral over a rectangular region. But what if that rectangular region is askew, like this parallelogram here? Well, it's not quite clear how to actually integrate over this particular region. You won't have your bounds for x is always from 0 to 1, because on this side of the parallelogram, x runs between 0 to 1, but on this region over here, x does not run from 0 to 1. X runs from 1 to 2, right? Same thing with the y coordinates, right? Generally speaking, y runs between this side, which is the line y equals 0, to this line, whatever the equation of this line is. I believe it's y equals x. So it's not quite clear. You don't have constant bounds for both your x and your y because you don't have a rectangular region that you're working over. You're working over a parallelogram. So what we do instead is we do a change of variables where we change the variables so that we then integrate over a rectangular region. So let's sort of map out the idea. So we talked a little bit about what change of variables would look like in one dimension. Now we should talk about what that substitution or change of variables would look like in 2 dimensions. So the general idea is that I want to find variables u and v that map from this region, and I'm going to just choose the unit square. So the vertices are 0, 0, 1, 0, 0, 1, and 1, 1. And I'm going to call this region S, right? So what I'd like to do is find what transformation maps this region S to the region D that I'm trying to integrate over, which I'll draw again. So 0, 0, 1, 0, 2, 2, and 3, 2. So that's sort of the general idea. And so this transformation, we often call it capital T. So the transformation T is defined from the UV plane so this is your domain, and transforms S to the XY plane, to region D. So the goal is to find what is that transformation that takes region S in the UV plane and transforms it to region D in the XY plane. We should probably specify X and Y. So oftentimes the transformation T has inputs u and v, which output your x and y coordinates, right? The inputs are your domain, outputs come from your xy plane, your codomain. And so generally speaking, x is given to us as a function of u and v, and whatever you get for the y coordinate is given to us as a function of u and v. So we often write x as a function x of uv, and y is a function of uv as well. Generally speaking, this transformation may or may not be linear. And what I mean by linear is that, in this case, because we're mapping lines to lines, we can think of this as a linear transformation, meaning that how we define my function for x and y will, in a sense, be linear, right? You can see here, region S, we're taking this side of region S, which maps to this side of the parallelogram in region D. So that line got mapped to that line. This side gets mapped to this side of the parallelogram. Line got mapped to another line. This side got mapped to this side of the parallelogram. Yet another line got mapped to another line. And finally, this portion and this portion, lines get mapped to lines, right? So in general, we can think of this transformation for this example to be, in a sense, linear. So what is it being a linear transformation do to help us? Well, that means that how we'll define our functions for x and y can be defined linearly in terms of the variables u and v. So x will be some coefficient a times u plus some coefficient b times the variable v. So this is a linear function in terms of u and v, the input variables. And it's written linearly where we have to find the coefficients a and b. Same for y. C times u plus another coefficient d times v. So if we use what the vertices get mapped to, hopefully this will give us a linear system that will allow us to solve for all four values a, b, c, and d. So let's actually do the algebra. So in particular, and I'm going to write down what each vertex gets mapped to. Here we have u and v. There's 4 vertices from region S that get mapped to 4 different vertices in region D via this transformation T. So let's go with the first ordered pair, 0, 0, gets mapped to the vertex 0, 0 in the xy plane. In the UV plane, 0, 1 gets mapped to 1, 2. Or sorry, this was 2, 2. 2, 2. So 0, 1 got mapped to 2, 2. 1, 0, this vertex here, got mapped to 1, 0. And 1, 1, this vertex up here, got mapped to 3, 2 in the xy plane, right? So I'm going to use this information to derive a linear system to solve for the coefficients a, b, c, and d. In particular, using the very first order pair doesn't give us much information because all you're going to get is that 0 equals 0. But if we use this to the second two, that is sufficient information to solve for the coefficients a, b, c, and d, right? You have an equation that comes from every coordinate, right? So you have an equation that comes from this x coordinate, a second equation that comes from this y coordinate, and then 2 more that come from the x and y coordinates of the second vector. So that's 4 pieces of information to solve for the 4 unknowns. So that's a linear system that we can solve for. So let's actually do the algebra. So very first equation I have, when x is 2, u and v are 0 and 1 respectively. So I get 2 equals 0 plus 1b. So I immediately get that b equals 2. Now using the y coordinate, I have that y is 2. Y is 2 when u and v are 0 and 1 respectively. So this gives us 2 equals 0 plus 1v. So both b and d, in this case, are both 2. Now using the second coordinate that I have boxed up here, same idea, right? When x is 1, I plug that into this first equation. When x equals 1, that came from the coordinates u and v are both 1 and 0. So when x is 1, u is 1. I get a plus v is 0, so that term is 0. So that gives us a equals 1. And then finally, when y is 0, I plug that into the second equation. And that comes from when u and v are both 1 and 0 respectively. So when y is 0, that equals c times 1 plus d times 0. So we immediately get from that equation that c equals 0. So those are 4 unknowns that we just solved for using the information from those two vertices and what they got mapped to. So we found our equations, right? X equals u plus 2v, and y equals 2v. So those are the equations from the linear transformation that maps region S in the UV plane to region D in the XY plane, right? So these two equations will give us the change of variables or the substitution that we'll require to actually evaluate this integral. Now there's a big question about what is dA. So we can think of A as the area and D is the change in area, right? So we went from region S, whose area we can compute, and that's just the unit square, so it has area 1, to region D, which is a parallelogram. We know the area of a parallelogram is base times height. And if we compute its base is 1 and its height is 2. So this parallelogram actually has area which is 2 units. So when we're thinking about this dA term, that really means when you're doing these change of variables, dA just tells us what the change in the area is. So we went from region S, which had area 1, to region D, which has area 2. So you would expect when you change your variables, your dA term, when you do the change of variables, would be 2 du dv. And so let's actually talk about that mathematically. How do we actually derive that? And there's this concept of the Jacobian that allows us to derive that. So let's actually define what the Jacobian is. So the Jacobian is defined as follows. Partial xy over partial uv is the determinant of this 2 by 2 matrix that has entries partial x with respect to u, partial x with respect to v, and then in the second row, partial y with respect to partial u, and partial y with respect to v. So you have to compute the partial derivatives of both x and y with respect to the variables u and v, and then take its determinant, right? So dA, mathematically speaking, is defined to be the absolute value of the Jacobian so you would take the determinant of that 2 by 2 matrix, take its absolute value times du dv. Right? So that's what dA is defined to be. And you'll see But that does match up with our intuition that dA really just represents the change in the area when you transform from region S over to region D. So let's mathematically compute those four partial derivatives, right? So for our example, we need the absolute value of the Jacobian, which in this case, the partial derivative of x with respect to u, that's just 1. Partial derivative of x with respect to v is 2. Partial derivative of y with respect to u is 0, and then with respect to v is 2. So when you compute the absolute value of the determinant, you get 2, right? So let's actually evaluate this integral. We'll do the change of variables. So x is u plus 2v, which I'm substituting that in. Y is 2v, so minus 5 times 2v, times dA, right? dA is the absolute value of the Jacobian, which we computed as 2, times du dv. Now let's talk about the bounds that follow u and v. We strategically chose this transformation so that we were able to write things in terms of u and v with region S, which is a rectangular region. So at this point, we know how to find the double integral over a rectangular region. As you can see, u and v run respectively between 0 and 1, right? So we can compute this double integral. Let's actually simplify this out. U plus 2v minus 10v, and then multiplying by 2, I think we get 2u after we multiply by 2, and then this should be minus 8v times 2 is minus 16v. And so now let's integrate with respect to u. Here we get u squared minus 16uv, and let's evaluate at the bounds. U is 1 and 0. When we evaluate, we get 1 minus 16v dv. Integrate with respect to v. V minus 8v squared, and evaluating at the upper and lower limits, I get 1 minus 8, which is negative 7, right? So we were able to evaluate this integral by doing a change of variables. Originally, it was quite unclear what your bounds for x and y were, but by changing the variables using this transformation t and rewriting it in terms of variables u and v so that you're now integrating over a rectangular region that we know how to find this double integral of and evaluate, we're able to now successfully use this substitution and change of variables in 2 dimensions. So that's all that I have for today. Thank you all for watching.